Hello, I'm Sviridov, and today I will present my work on AI-assisted assessment of cloud gaming QoE. Differently from traditional gaming, in cloud gaming, games are run on remote servers and only the render of the game is sent to the player in the form of a basic video stream. Users are allowed to interact with the game by pressing buttons as they would do with a normal game. The main issue with cloud gaming is that it combines elements of traditional online gaming, which requires low bandwidth and low latency, and video streaming services, which require high bandwidth but low latency. Combining the two things together inevitably leads to the so-called input lag. From the networking point of view, one way of solving issues with the latency is to provide quality of service guarantees for game streams. Unfortunately, there is no universal set of quality of service parameters that would fit all games. You see, games come in many genres such as fast-paced shooters and slow-paced strategy or simulation games, and of course latency has different impact on the game depending on its genre. To solve this issue, one must perform fine-grained quality of experience assessment in function of network parameters. Traditionally, game QoE assessment is performed by measuring the mean opinion score or the performance of human players playing a given game in a controlled environment. This approach is known for being unreliable and leading to no repeatability and noisy data, which is mostly the fault of human subjects employed in the experiment. These limitations can be overcome by substituting humans with bots, but this solution is still quite expensive because to develop bots one must have access to the game engine and have in-depth knowledge about each single game. Our idea is that of training bots using AI models by having as input just the raw video data of the game, similarly to how a real human would do. To test our idea, we considered 3 Atari games and we trained 3 different AI agents using the DQN deep reinforcement learning algorithm, which exploits only the visual game frames. We were able to achieve human level performance for our agents in under 5 hours of training, and to test their response to network conditions, we plugged them in an emulated cloud gaming testbed. We deployed the AI agents at the hosts and made them interact with a game server which was sending game frames over an emulated network. This network was characterized by per frame lag probability, and per keystroke drop probability, similarly to a real network. We then measured the average normalized in-game score achieved by each agent in function of network parameters. What we observed was that different games have a different response to latency, which is in line with the previous discussion. Notably, Sequest was less sensitive to network latency in respect to Beam Rider and Breakout, both in the case of constant and probabilistic latency. Now, knowing this information allows us to define the quality of service metrics we were talking about for each individual game. As an example, we can define an in-network traffic prioritization scheme which is able to maximize the average in-game score across different game sessions. Yet more complicated quality of service mechanism can be designed to use this information. Of course, such methodology requires further investigation. A key question is whether AI agents are representative of human behavior. We are trying to answer this question by letting people play the 3 games we consider for our experiments under different network conditions. And you can contribute by going on this website, atari.sviridov.io, and play some Atari games while having some fun. We're also investigating how such approach applies to more complicated games, and we are currently experimenting with some 3D games such as Doom, and we're getting some great results. And finally, we're investigating deep reinforcement learning algorithms which incorporate the notion of lag to emulate the behavior of more experienced players which can tolerate the presence of the lag. That's all. Thank you for your attention.